Hello, welcome back to today's stochastic processes class. And then today we'll be checking examples on Chapman Kolmogorov equation. Okay. Alright, in our previous class we checked Chapman Kolmogorov equation, we derive it and we also prove it. This is a combination equation of a Russian mathematician and a British mathematician. So we'll be implementing this equation to solve some stochastic process question, especially times homogeneous equation. Let's look at this example. We have the transition matrix for people voting for candidates from various political parties in an election yearly is given below. So assuming there is, okay, let me explain the transition matrix. We have this D represents Democratic Party, R represent Republican Party, while I represent Independent Party. So the probability that those that vote for Democratic Party will vote for Democratic Party in the next year is 0.6, while those that will vote for Republican for the next year is 0.3, and for Independent is 0.1. However, those that vote for, if the current voters are Republican, they vote for Republican, the probability that they will vote for Democratic in their next election is 0.3, while for Republican is 0.6, while for Independent is 0.1. Lastly, the probability that those that vote for Independent Party in this current election will vote for Democratic candidate for the next election is 0.1, while for Republican 0.2, and for Independent is 0.6. So we have, assuming there is an election every year, so that the transition period is 1 year. So we have two questions to solve using Chapman Kolmogorov equation. We have find the probability that a person who votes Democratic in the current election will vote Republican in the election 5 years from now. We have to find the probability that a person who votes Democratic in the current election will vote Republican in the next election, in the election 5 years from now. So, and we also have find the probability that a person who votes Republican in the current election will vote Independent in the election 7 years from now. So with the help of Chapman Kolmogorov equation, this equation will be easy for us to solve. Let us start with solution number 1. So the question is that the probability of those that vote for Democratic currently will vote for Republican in the election 5 years from now. That is over 5 steps. The probability of transiting from Democratic to Republican over 5 years. So, and we know that our Chapman Kolmogorov equation, let me write it somewhere, is giving us, let me change my pen and write it somewhere here. Chapman Kolmogorov equation is giving us probability of moving from I to J over n step is equals to summation k, we belong to the state space, and probability of moving from I to K over R step, and probability of moving from K to J over n minus R. So we are going to partition it. So making use of that method here, we are going to, since we are moving over 5 steps, so I will just partition this to, I will make my R to be 3, and that, okay, I'll take R equals to 3, and n minus R, which is 5 minus 3, that will be 2. So I'm going to partition to 3 and 2. The steps is 5, but with the help of Chapman Kolmogorov equation, I can partition it to 3 and 2. That is, I'm going to have summation k, belonging to the state space, probability of moving from I to K over 3 steps, which is my R, and probability of moving from K to J over n minus half step, which is 5 minus 3, which is 2. So what I need to do now is to find, don't forget my transition matrix is giving us, let's take that again. We have 0, 6, 3, 1, 0, 6, 0 0.3, 0 0.1. We have 0, 3, 6, 1, 0 0.3, 0 0.6, 0 0.1. And lastly, we have 0 0.2, 0 0.2, 0 0.6, 0 0.2, 0 0.2, 0 0.6. So what I need now, I need p raised to power 3 and also p raised to power 2. Okay, so p raised to power 3, that is, we are going to find the cube of our transition matrix P. So you can do that, as you are going to multiply this over times 3. Okay, because I need raised to power 2, then first of all check p raised to power 2 and not it. Let me have p raised to power 2 here. P raised to power 2. So, in order to make it faster, I want to make use of my calculator here, but you can do it, but because of time, so, trying to do the calculation here. We have we have 0.6, 0.3, 0.1, 0.3, 0.6, 0.1, 0.2, 0.2, 0.2, 0.6. Okay, so the square of this now will give us 0.47. We have 0.47, 0.38, 0.15, 0.38, 0.47, and 0.15, and 0.3, 0.3, and 0.4. Okay, so I need the p cube also. The p cube. So just multiply the p square with one of the transition matrix, then you have the p cube. So you have 0.426, 0.399, 0.175, 0.399, 0.426, 0.175, and 0.35, 0.35, and 0.3. Okay, so taking this formula I'm working with, I only need the, so let me write this. I'm going from D, okay, here should be D, and here should be R. I'm moving from D to R. I just partition it here. So what I need now is the probability of moving from D to K. Probability of moving from D to K. I'm going to write the whole thing. We have probability of moving from D to R over 5 steps is given as probability of moving from D to K over 3 steps times probability of moving from K to R over 2 steps. Correct. Okay. So the probability of moving from D to K, since this D is a that D notation is for your row and this R is your column. So we need the row of D in P raised to power 3. Don't forget we have D, we have Ri, we have D, we have R, we have I. So the row of D in P raised to power 3, that is all what we need. And we shall this is the row of D. This is the row of D. When I pick a nice column, sorry, this is the row that for in P raised to power 3, the row of D in P raised to power 3 is this, so we just write it out. That is all what we need. We don't need the whole element 0.426, 0.399, and 0.175. So next we need the column in P raised to power 2. We need the column of R. It is DRI. So the column of R here is this, and that is all what we need. That is in the column matrix. We have 0.3, 0.47, then 0.3. So we add up this together, then we have our result. We have 0.426 times 0.38. Don't forget your matrix rule in multiplication. That will be 0.426 times 0.38. 0.426 times 0.38 plus 0.399 times 0.47 plus 0.175 times 0.3. Then we have 0.40191 as your result. So our Chapman Kolmogorov equation make our calculation very easier, especially when you have to do with a large number of steps. What just you need to do is to partition it. So let's check the second example. The second example, we have to find the probability of moving from R to I over 7 steps. P to R over 7 steps. Solution 2. Probability of moving from, again, let me check that, R to I over 7 steps. Likewise, I'm going to partition this to 4 and 3. That will be summation K, state space. Probability of moving from R to K over 4 steps, and will be probability of moving from K to I over 3 steps. So, and I know that P raised to power 3 equals to, from the previous calculation, and to get that again, P p raised to power 3 we have 0.426, 0.399, 0.175, 0.399, 0.426, 0.175, 0.35, 0.35, and then 0.3. That the transitional matrix multiply over into 3 places. So p raised to power 4 now. With the p raised to power 4, we have 0.413, 4103, 0.4022, 0.1875, 0.4022, 0.4103, 0.1875, 0.375, 0.375, and then 0.25. So now, so the first is probability of moving from R to K over 4 steps. Look at this, so D R I, D R I, so we applicable to this D R I, D R I. So in my p raised to power 4, since this R, this notation of R is for rule, so I need to find the rule of R, which is this. So that is the element I need in that p raised to power 4. So I have 0.4022, 0.4103, and 0.1875. And then lastly, I need the column of I in p raised to power 3, which is this. Column of I in p raised to power 3. That is 0.175, 0.175, and 0.3. So the next is to multiply it and then find the summation probability of moving from R to I over 7 steps. So we have 0.022, 0.22 times 0.175 plus 0.4103 times 0.175 plus 0.1875 times 0.3. So we have 0.1984375. So that is how to implement the Chapman Kolmogorov equation. Very helpful in order to check the transition from one step to the other over higher number of steps. Okay, thank you for watching. My name is Sunday. See you in the next video.